Now, what is the polynomial interpolation? Polynomial interpolation. This, imagine that you're having um, a data set with a lot of points and yeah, a bunch of points, and you want to make a prediction for it. So what you want to be doing is to create a function, in this case, a polynomial function that with a certain amount of data that will be p elevated to x, which is equal to x elevated to some power of, let's say, to some power of n plus um, the coefficient 1 plus coefficient 2 elevated to n minus 1 plus all towards coefficient of of 1 plus x elevated to x elevated to 1 plus x, this will be x n, x n, and x n plus 1, and x plus minus 1, x 1, and this one is x 0. That is a polynomial equation. So what we are going to be doing is towards getting the approximation of these set of points. How can we get them? Well, first of all, why are we getting this approximation? And you'll be asking, your question is correct, man. So what you're trying to get through all of that is, why not to get an approximation? What can we do with an approximation? Well, anything. The possibilities is just that we can make the prediction. This is the basic understanding for the regression and the prediction in all of machine learning. This is the starting point. The starting point even for simulations, that from a basic data set that you already have and from data that is collected in and stored in data centers, you can get predictions. That is it. You're having, normally, for example, in data centers, you're having data, you are getting it towards the polynomial approximation that we mentioned, and we are getting a prediction. Now, what is this? What are the methods to get them? And what are the limitations towards it? So the ways to get through it, it will be using Lagrange polynomials, divided difference interpolations, linear least square methods, and non-linear least square methods. We'll explore each one of them. Moreover, however, I want to point something that are some limitations through these things. And is that even though we have a certain amount of data, for example, all these points in here, we can make an approximation based on it. But what we don't know is that what will happen if we are limited through a certain range of data or a certain domain, and moreover, on time, there is more generated data that our approximation will just go further on it. And the only thing that will be a limitant, but we can't deal with it, is just for you to notice it, is that there could be a different way of getting it. So for example, what about if our next data go towards here, or our previous data goes here? So this doesn't mean that you need to be doing that. You just gotta mention the limitation on the range of data that you are having now, but it will be important for you to mention moreover if or even to make that is why it will be important to make the updates towards getting all this information that you're not computing to making the first model machine learning model or even the first polynomial function that you are getting. Okay, now that we have set the limitations of it, let's start exploring the polynomial functions with Lagrange. It will be getting, um, let me just share now through the change of screen. So basically, let's start exploring more on how to get them, and next we'll explore on the algorithms. And all right, so let's explore the polynomial interpolation. I don't know, I don't know why it's not computing, so I'll pass. Perfect. But, well, um, so let's explore now. What are the first numbers? What we'll look to make is to get the algebraic method. This will represent that given a number of set of values, what certain mathematicians have done is that they computed something that was called Lagrange. Well, this one was a method that is based on the algebraic method, but let's start exploring what is Lagrange. Basically, what this means is that you're given um, so you will be given these values. You will be having Lagrange 1, Lagrange 2, or well, these are the set of points that you're having. And now what you want to be getting is to get a function p, let's say this is x1, this is x2, this is x3, x4, and x5. And wow, how can you very simple. What Lagrange, this mathematician mentioned, is that what about if you create a function where you're having a sum of the x1, in this case, while you are in J here, so the J1 plus a Lagrangian. This value, Lagrangian 1, plus L plus Lagrangian 2, which is multiplied by J2, plus Lagrangian 3 multiplied by J3, all towards the sum of Lagrangian n multiplied by Jn. This is actually what here is in this function. So what this means is that what they are trying to get is a way to make the sum of all the values, but once you are having certain x, you want to be getting the exactly x that you have been getting. The exactly value for j corresponding to the j to the x that you have been given. So what this is important to notice is that the Lagrangian will have possible two values. It will be 0 or it could be 1. This means that if it's 0, all these values will be multiplied by 0. Imagine that they give us x1 and they ask us to get the j1. Well, all these values, if we multiply it by a Lagrangian 0, then they will be 0, and the sum, it will just give us this first value for the j1, which was the Lagrangian one. And this is really easy. And then you just gotta search for how to get a value that computes that. How can we get a Lagrangian that makes that estimation? Well, eh, really simple. The Lagrangian, what he's making is just that the Lagrangian n, it will be equal to the x value, or well, actually, it will be equal to the multiplication. This means that much easier. Let's go with the formula. So I'll explain what's the formula. You are having all the j's computed here plus the multiplication. This part over here is what is called Lagrange, the Lagrange number. This is the multiplication for the current value of x minus all the different values, not from the current x that you have been given. So you will go all the different values divided by the difference between the current value of the same value that is I from j, meaning that for every single one of the points, for example, let's remember we have the points over here. So if we are at this point over here, you want to be having the same x value over here, and this value, if we are setting this was the x value that they give us to us. So this one was x1, and for these other two, what will be happening is that they will be eliminating, because the difference between this value from here and the next value that uh, from j, which is the same from here, it will be equal to 1 only in the case where all the values is being multiplied for this one over here. But in case the other part of the equation, for example, if we are having this here, what we are going to be having is j2 multiplied by x, and in this case it was x1 because that was the value that they gave us to us, minus x, let's say minus x2 divided by x2 minus x2, which this will become to 0, and then therefore we are having 0 over this equation, and then this is being eliminated. Well, this is actually, it goes to an error, and the thing is that it won't be able to be getting it, and the only value that will be computed is for the first one. Now, that was a really interesting method. However, because of the amount of Lagrangians that you need to have, it's expensive. So what Newton mentioned it was that, okay, let's stop doing that one over there and let's try to simplify it and make it an optimal way. Thus, what he created was an idea for just computing the divided difference. This means that what he looked to do, it was that based on on a certain approximation, create on a certain point, create the tangent instead of getting the Lagrangians. So you will have the first tangent, or for the difference between this one, these 2 points, you are getting the multiplication for the tangent value or the slope that you are having to get the next point in the value in the j position. So therefore you are gonna have the derivative for every single one of them, and these ones was created by Newton. He presented two different ways of getting it. First is the divided difference by getting the slope, the multiplication of the slope for in a forward position, or you can be getting it in a backward position. You are having this, then this, and then this. The method is a little bit better explained through the notes, but basically that's the idea. And the idea is based on the equation that Newton presented to us for getting the estimation of the next point of every single one of the next iterations. This will be really useful for the Euler equation as well, and which will see it much more later in our course in differential equations. But for now, let's continue with it. The the next point is just the linear equations, the linear least square method. This is an optimization problem. What we're having through here is a way to get how to minimize the error. What's the error in this case? It will be this one over here. Oh God, what just happened? Um, okay, this over here. This is our loss function in this problem of optimization. If if you have no understanding on optimization, it's really simple. You have a set of a valley of mountains. Imagine that you're in a valley of mountains. You can see all over the mountains, and you can see you like you are set on, for example, let's not put it here. Imagine here we have the Everest and the other mountains around it. And we are looking with our eyes. Here we are seeing with like a telescope, and well, here's not the best drawing, but we we are seeing through with a telescope through the mountains. So basically, the optimization is how and what's the shortest path towards getting to the minimal point or the maximum point. Okay, now once we remember that part of optimization, how can we get the critical points towards minimizing the error between an approximation of linear equation, in this case, the a plus x A multiplied by X plus B. These two parameters over here are called estimators. The estimators of the linear equation that will be estimated towards doing the approximation of the points that we're having. You will be mentioning like, why do we are trying to get through this, the optimization of that equation? Well, it's really simple. This is the difference from every single one of the points in our graph related with the line that we had just created. So that's it. How can we do this? Well, with in this case, it was an analytical process that they computed for getting the optimization problems. However, through numerical analysis, we'll see much more faster ways to get it. Basically, in the analytical way, it's that getting the errors, the logic difference that are gonna be getting through all the j, the real value of j minus the linear approximation that we have generated, elevated to square. This will be the root or the square error. This, this is actually the sum of the mean. This is the sum of the square error, yeah. You are gonna be getting the differential value of the loss function with respect to the evaluator of A. And same case for here. You're getting a partial derivative with respect to the loss function with respect to the value of B. What does that mean? What is a partial function? Well, very simple. So let's say that you have the value that we have just presented, and you will have here the loss function and here the variable that you're gonna be getting. So you have A and you have B, sorry, and you have the loss function. How can we minimize this point? How can we get here? Well, what the partial function is doing is that it's getting through through searching through this way, what is the shortest path towards getting to the minimal point? If imagine in case of going through that way, we start exploring this way, well, we're never gonna be getting here. So what they are doing is through the tangent of it, they are approximating to the minimal point, or also known as critical points. So once we have understood that imagine it's just like a mountain climber looking to get to, or in this case, like you have a ball and and you throw a ball over the through the ball. What is the fastest way to get to the minimum point? Imagine that you could be having two different points and it could be getting here, or it could be getting here, or here, or here. So how can we get as fast and not explore through this way, instead explore through this way towards getting to the minimal point? Okay, basically, this is through doing the derivative of the loss function with respect to A. We get this equation of here, which is 2. We get this equation from here, which is, as you can see, 2 goes in here, and the multiplication of x, it goes out of it here, and that give us the current value of this equation over here. Same case for b, instead of getting the output of the derivative will be -1, because this is uh, actually getting from here, it's multiplying here, and you get it out of the function. That is the derivative of the initial function with respect to the partial derivative with respect to b. Now, what are the critical points? We need to equal this to 0 towards the difference between every single one of them. How can we get it to the critical point, right? Where the derivative with respect to the last function, it goes to the minimal point, and same case with the estimator of b. When we have Once we have these two equations from here that we have equal to 0, then we get the estimators um, by computing the equation by so basically what we have done here is just to do the multiplications, and then this part which was negative, we pass it to the other side of the equation, and there we have it. We have the two different equations. This correspond to this one, and this correspond to this one. And now, how can we resolve these linear equations? Well, we have two variables, which in this case is a and b. Really simple. We can use Cramer's rule to get it through the multiplication of this one plus this one divided minus the multiplication of this one by this one. This is the determinant. This is the way to get a determinist. And then we just got, once we have gotten the determinant, once we have computed the determinant, we need to apply the same thing, but now with the difference, or with the multiplication of this value from here with this value from here, or well, this one plus this over here, and this one from here plus this one from here. You see here that square, and same case, and we divide it by the determinant, which, as you can see, the determinant is worth noticing that is the covariance of it, meaning the variance, the variance of it. So that means that we are having a hypothesis test that the variables of or from this here, we are gonna be looking if it's possible to compute it, to get the approximation. All right, so that's it. The final point now, let me share the last screen from here. All right, so I have explained Lagrange polynomial. It's the same, divided difference is the same, and linear square is the same. What is different is the how to get the polynomial squares. And this one is really interesting because instead of getting through the Cranber's rule, the resolving the system of equations, we are doing it in a way that we have multiple variables. It's not just one, which is this case, it's x. Instead, we could have a matrix of x variables. Thus, resolving these equations over here, it's possible to get that. Where, especially because you can't use Cronberg's rule when the degree of n is bigger than than 5, sorry. Then, to get the root, to find the roots, we need to apply the equation system of ax equal to lambda x. What does this mean? It's just the principle of linear algebra, which we'll be seeing much more over on course, but it's important for you to notice why are we applying it. So as you can see, the lambda function is useful to find the roots of a system of equations. So imagine that instead of having to resolve through Cranberg-Lumbergs, we can do this to make an approximation for not just one variable and to get a linear approximation, but instead to get a polynomial approximation of least square roots. So it's worth noticing that the eigenvalues, they are only useful for computing the results in a square matrix. However, applying singular value decomposition, it's possible to get through a rectangle matrix. Thus, for applying a polynomial equation of b0 plus, or having this polynomial equation, it's possible to compute the um, the through this equation through the coefficient of vectors. This way, we can get what will be every single one of the coefficients corresponding to this equation over here. So to get the value of b0 towards bn. Finally, we'll explore the non-linear least square methods, but just as a brief, because this will be exploring also in statistics. Basically, what this means is that using a kernel Gaussian function, we are gonna be setting some weights, and those weights are gonna be an approximation towards the value that we wanna be having. But in this case, is that they are using, instead of doing trying to compute the optimization with um, with a polynomial equation, here they are computing it with kernel with the probabilistic distribution kernels. Thus, the approximation to the problem, it's much more smoother in this case. Why is it important? Well, this is a principle of machine learning. In machine learning, what it's what is important to notice is that the concept of um, one concept is is just to get um, well, basically is that you want to have the approximation not to be so tight to your data points, because if you have it here like super tight, then when you want to make the prediction to another variable, probably this won't be really close to it. Instead, you wanna have it um a little bit more flexible, so that when you have another approximation, because probably here will go towards here, you wanna have a less error. This problem, it's just um, the overfitting. Here we're having overfitting, and here is good, for example, and we can be also having underfitting. Sorry, underfitting. Underfitting is basically, imagine that we have these variables from here, only it's like this is not fit at all. But this you don't want to have it very fit, and you don't have it underfit. You want to have it like the correct fit. This is the correct fit. So basically, that's it. That's the principles of polynomials. I hope it makes a lot of sense to you. I know this video it's a little bit confusing. I'm starting recording these videos. I hope you find it useful, and we'll keep going. We'll keep going. So in the next video, we'll search on root finding. In this case, imagine, which basically is just from a function now. How can we get what's the approximation to zero? And that's it. Thank you very much for today's lesson.